Alright, so some fundamentals of simple harmonic motion. You got like a pendulum, like a clock, we all know what a pendulum is, and then a spring. So one of the basic equations is for the frequency, which is 1 over the period, and that's in hertz. Another equation for it is the angular speed, or angular velocity, omega over 2 pi. Omega is also equal to 2 pi over the period, or since it's 1 over t right here, that can be just 2 pi times the frequency. So for a graph of simple harmonic motion, from the this axis to the top of it is called the amplitude A. Between the two antinodes from the tops is called the period, the t, and every time it touches the axis, it's a node. To find the velocity, when it's on the axis, it's 2 pi times the amplitude over the period. Or since it's 1 over the period, it's also 2 pi times frequency times the amplitude, which is also equal to your omega A.
Alright, so here we have a notebook hanging from a spring, which is actually a rubber band. And right now it's at equilibrium, but when I pull it down to an amplitude A and release it, it'll oscillate. And what's important to note is that right at its equilibrium mark, while it's going up, it only has kinetic energy, and then everywhere else it has some sort of combination of kinetic and potential energy, except for at the very top.
Okay, so this is a little drawing of what was happening with the notebook on the door handle. So here it's at equilibrium, and we found that it was 0.2 meters from the edge of the door handle to the edge of the rubber band. And then when we stretched it to x, which is 0.2 plus A, or L we call it, it was plus 0.07 meters, so 0.27 meters. So that would the 0.07 would be the displacement because of the difference between the equilibrium and stretched. And so at equilibrium, the weight and the force of the spring are equal because it's not moving up or down, so therefore the net force is equal, so it wouldn't be moving at all. So now that we have the displacement, and also because we know that the weight and the force of the spring is equal to each other, we can solve for the K, which we do here. So we find that the notebook mass is 0.5 kilograms, and the acceleration due to gravity is 9.8 meters per second squared. So weight equals energy, so is 0.5 kilograms times 9.8 meters per second squared. So we found that the weight is 4.9 newtons. We then related that to Hooke's law, which is negative k times displacement. So we had negative k times the 0.07, which is displacement, equals the 4.9 newtons, which is the weight. Then we solved for k, and we got negative 70 newtons over meters.
So we're going to solve for the velocity when the spring oscillates. So the spring always has potential and kinetic energy at some point in the system. The potential energy is 1/2 times the k and the a squared, and kinetic energy is 1/2 mv squared. The energies equal each other. 1/2 ka squared equals 1/2 mv squared. When we solve for v, we get v equals the square root of k over m times a. We solved for k, which was 70 newtons over meters. The original mass was 0.5 kilograms, and the amplitude is the displacement L, which was 0.07 meters. So the velocity comes out to the square root of 70 over 0.5 times 0.07, which is about 0.83 meters per second.